Should be fine.
Okay, I think live stream is working because I can hear myself. Okay, still hear myself. Okay, can you hear me well now? I think I fixed the echo problem, hopefully. Okay, so let's get started. Yeah, sorry for the delay. We were in the earlier computer architecture lecture and it ran longer than expected. And also my computer was running out of battery, so and somehow the infrastructure doesn't allow me to charge the battery, so that's why I'm back to my office, unfortunately. Yeah, but hopefully we'll have a shorter class today. That's my hope. But feel free to ask questions. I guess I want to do one thing over here. Maybe I'll change my background. Maybe. Okay, now you can see an office also. That's good. Okay, cool. So let's get started. So we're going to talk about another example paper review today. And I picked memory channel partitioning. You can also find this online, but recall that you have a lot of, we were doing example paper reviews and presentations and hopefully discussion as well. Last week we did the row clone and processing using DRAM, and there was a lot of discussion. So let's keep it like that. Let's have a lot of discussion in these lectures. Feel free to ask questions. And before that, Mohammed did the gatekeeper plus other things in genome analysis that are quite exciting. And remember, you can also find some other example reviews. This is 2019. Minesh did this Reaper paper, which is about data retention errors and their handling in DRAM systems. And I would recommend you take a look at it. It's another example paper presentation plus discussion. And then also you can see how presentations went by students from last year. These are some students who were okay with being live streamed or recorded. And this is one example presentation. You can see how it really happens in class as well by fellow students. This is another one where we discuss compute DRAM. Another one, actually there are two presentations in this one. You can see it's about 2 hours over here. And basically you have a lot of resources to see how past presentations have gone and how past discussions have gone, in addition to what we're going to do today as well. I think this is the last one. And also, if you're interested in having yours online, I know different people have different levels of comfort for this, but we will ask you if you want to be live streamed or uploaded, even if it's not live streamed, and you can let us know. Okay, I think with that background, let's do this other example paper presentation. And again, feel free to ask questions. Again, I will follow the same structure that I followed in the last meeting. Again, I have the, I guess, luxury to review my own paper and have a lot of the hindsight on it, as well as having done research in this area for more than a decade, on the topic of this area for more than a decade, actually more than 16, 17 years or so. I can also give you a broader perspective of how this paper fits into the literature. Okay, so let's get started. Basically, I'm going to first present this paper that was published at Micro in 2011, almost 10 years ago. The title is Reducing Memory Interference in Multi-Core Systems via Application of our Memory Channel Partitioning. And you can see the authors on the slide. Again, I'm going to use slides developed by my first PhD student, actually, Lavanya. She was my first PhD student to graduate, and her PhD thesis was on enabling controllable multi-core systems, and memory controllers were certainly one topic that she worked on heavily. But again, as I said, I'm going to use the same structure. We're going to start with background, problem, and goal. And this paper is targeting main memory bottleneck, specifically the memory channel bottleneck. Main memory latency is long, and because of this, whenever core requests something from main memory, it stalls and its performance and the system performance degrades. And when you have multiple applications running on multiple cores or multiple different threads, they share the main memory and they interfere with each other when they access main memory at the same time. And okay, yeah, somehow my Zoom is slow again, but basically one application may be sending requests, another application may be sending requests, and they may be interleaved with each other. And this inter-application interference degrades system performance. And the problem gets exacerbated due to when the number of cores increases, because now you have more pressure on the memory system, and the off-chip pin bandwidth, main memory bandwidth essentially, is limited. And that's many of the systems today. As we discussed at some point, we can put many computation units on a single chip or even on a single wafer today. And we have a lot of computation capability that also generates a lot of memory accesses because we're very data hungry. But the bottleneck between the chip and the memory chip, the processing chip and the memory chip, is essentially a big bandwidth bottleneck that limits how many things you can transfer at what rate at a given time interval. As a result, the interference effects get exacerbated because one core can delay another one for a really long time because of this interference on the limited bandwidth channel. Okay, hopefully that's clear. I mean, you've seen something like this also last time when we talked about row clone, right? Although row clone is targeting specifically copy and initialization operations and reducing the interference due to them and also the performance and energy impacts of them. Here, we're going to look at the general topic of interference. Any operation can cause interference. Any memory access can cause interference to other applications. So the goal of the work is to mitigate inter-application interference. And the previous approach has mainly been, before this paper, to do application-aware memory request scheduling in the memory controller. I'm going to give a description of the state-of-the-art approach before this paper and how it handled request scheduling. So this is memory controller-based. Memory controller hardware needs to change. And this paper provides two approaches. The first approach is to partition the channels so that you reduce the interference or mitigate the interference, by partitioning the channels across applications, such that applications that go to different channels don't interfere with each other as much. And the second approach is really take advantage of channel partitioning as well as memory request scheduling at the same time by combining them in a simple yet effective manner. And this is called the integrated memory partitioning and scheduling technique that we will discuss. Okay, so that's a high-level overview of what will happen basically. Okay, background, I think you've seen this before, but let's go over it again. Basically, if you look at a memory system, it has a memory controller, and memory controller contains essentially controls one channel. And on the other side of the channel, you have a memory chip, which may consist of multiple banks. And each bank has a row buffer. And row buffer essentially caches the latest row that was accessed in that bank. This is required, basically. You need to be able to sense the row, right? Like we discussed in row clone, for example. Okay, and there are multiple banks. Banks are two-dimensional structures, rows and columns. And in order to be able to access a row and a column, a particular address basically in a bank, you need to be able to bring the row into the row buffer, I mean, they activate that row. And once that row is inside the row buffer, the accesses to that row are fast. And that's the animation of the activation, as I discussed. Okay, existing memory controllers actually take advantage of this row buffer. Basically, they use a scheduling policy, existing memory controllers at the time. They still are based on this, but they have more quality of service mechanisms today. But at the time, they use a memory scheduling policy, memory access scheduling policy, or memory request scheduling policy that reorders a request in the memory controller such that row buffer hit requests are prioritized over other requests so that you can maximize the utilization of the row buffer, meaning hit rate of the row buffer. Because again, row buffer accesses are fast. If you need to activate another row and bring it into the row buffer, then that access is slow, right? And to maximize the DRAM throughput, they try to prioritize row buffer hits. And all else being equal, the second prioritization order is based on the age of the request, meaning oldest request. When did the request arrive at the memory controller? Okay, so basically, this is not application aware clearly, right? This tries to maximize DRAM bandwidth. And as a result, it's not application aware. It's unaware of the inter-application interference that's happening in DRAM. And prior works actually targeted this problem. but not in the way this paper targets the problem. So that brings us to the novelty. So basically, let's talk about how prior works targeted this problem. Prior works, there are many prior works on especially application-aware memory request scheduling. And this paper has a nice survey of them in the related work that I'm not going to go into. But generally, application-aware memory request scheduling techniques treat different applications differently. You can think of this as threads also. So when I say application, you can also think of them as threads or cores. But basically, memory controller monitors memory access characteristics of different applications or different cores or different threads. It ranks the applications based on memory access characteristics and prioritizes the requests based on that ranking. And prior approaches propose purely hardware solutions to this in the memory controller. Memory controller monitors, ranks, and prioritizes. So let me give you a concrete example as to how this is done. This was the state of the art in 2010. And this, remember, the memory channel partitioning paper was in 2011. This is still a nice idea, I think, thread cluster memory scheduling. The idea goes like this, basically. You have a bunch of threads in the system. You can also think of these as applications, assuming an application is a single thread, right? That's not always true, but the later works also tackle that, which we're not going to go into. So you have a bunch of threads in the system executing on different cores. The memory controller classifies these threads as memory non-intensive and memory intensive based on some threshold. So this is the clustering part. You cluster the threads into non-intensive cluster and intensive cluster based on their characteristics. Characteristic is memory, basically how many misses do you generate per instruction, for example? What is your memory access rate, in a sense, per instruction? And there are some intensive applications that require a lot of memory accesses, and there are some non-intensive applications that don't require a lot of memory accesses. Then the memory controller clusters them into two groups and prioritizes the non-intensive cluster. And the reason for this is these applications, these threads, generate requests once in a while, not often. Once in a while, they generate requests. As a result, they have very high potential for making progress, let's say. If this request, let's say you generate requests once every, I don't know, 1 millisecond. If that request gets serviced quickly, you keep your core busy. But if that service request gets delayed because of many, many other requests from some other intensive applications, this application that would otherwise easily keep its core busy gets delayed. As a result, core utilization reduces. And the idea is if you prioritize the requests of these non-intensive applications, you improve throughput, system throughput, by allowing the cores to be utilized. And you also don't interfere with other applications that much because these applications are not intensive, meaning they don't generate a lot of requests. They generate requests once in a while. So that's the idea, basically. Prioritizing the non-intensive cluster improves system throughput significantly because it makes sure these applications that have a lot of potential to make progress in computation make progress, as opposed to getting delayed behind heavy applications. And also, it doesn't impact heavy applications significantly. So you can think of this analogy as mice and elephants, right? In fact, that analogy has been used in systems before. You have a lot of mice and you have some elephants. Elephants are the intensive ones. Mice are the non-intensive ones. Mice can move really fast, assuming that elephants give the way to those mice, right? And in this case, we're prioritizing the mice so that they don't get destroyed by the elephants. And mice cannot destroy the elephants unless there are a lot of mice, right? That's the idea. So if it's only a few mice, it's very hard to destroy the performance of the elephants. Okay. And the paper actually has very nice descriptions of this mice and elephant effect. In fact, a prior paper, Atlas paper, does that. Okay, I have already given you basically. So, but basically, what do you do inside each cluster? So I've already given you that this cluster, non-intensive cluster, is prioritized over in the intensive one. But what do you do to the threads inside each cluster? So inside each cluster, basically threads are ranked. So in the non-intensive cluster, higher priority is given to the smaller threads, meaning smaller threads, meaning less intensive threads. So the least intensive threads gets the highest priority in scheduling. If there's a request from the least intensive thread versus a more intensive thread in terms of memory intensity, MPKI, misses per last level cache misses per instruction, then the one that is less intensive gets prioritized. So there's a ranking order. And the paper analyzes this, and I'm not going to talk about it because there's prior work. Right? For the other threads, These are the elephants. So these are mice. Between the mice, prioritize the small mice, because small mice may be faster, right? And again, prioritizing the small mice doesn't hurt the larger mice, hopefully. Between the elephants, this doesn't work very well. Basically, you have huge elephants, let's say 3 elephants like this. If you prioritize one over the other because of some smaller difference, let's say one elephant is slightly larger than the other elephant, and you prioritize a smaller elephant, but the larger elephant gets denied service significantly in this case. So basically, you employ a fairness-based policy over here. Elephants take turns to go. Basically, these highly intensive threads, they take turns to access memory. Their bandwidth is basically partitioned. So it's a round-robin scheduling scheme to provide fairness. And this is also good for throughput, as this paper shows. So that's the idea. That's the state of the art. Of course, I described it in a little bit more detail than what I would normally describe, but hopefully this gives you a lot of insight into what's happening in a memory scheduling policy that takes into account applications' intensity levels and characteristics. There's more that goes on in the paper that I'm not talking about over here, because you don't always want to do round robin over here. Sometimes you want to distinguish between the characteristics, but I'll leave that for the paper, because the access patterns of different applications, different elephants may be different also. Some of them may be random access, some of them may be streaming access, and you may want to prioritize, let's say, nice applications over others. Okay, so that's thread cluster memory scheduling, and you can read the paper. This was it's one of the important papers in a series of memory scheduling papers that were presented in, let's say, between the time frame 2008 to 2012 or 13 or 14. Okay, hopefully that's clear. If there are questions about this, let me know. Now, this paper is not about memory request scheduling per se. It basically analyzed the advantages and disadvantages of this sort of memory scheduling techniques in general. Was there a question? Did I miss a hand? Okay, I thought I saw a hand, but good. So basically, advantages of this sort of application of a memory scheduling technique is clearly it reduces interference between applications by reordering the requests, right? Prioritizing some applications over the others. And it does improve system performance, it was shown. It does improve system performance, it was also shown. But the goal of this paper is not fairness per se, so it's going to be mainly throughput oriented. So we're not going to talk about fairness. But of course, there are disadvantages also. Like any idea, there are advantages and disadvantages. One disadvantage is that this memory scheduling policy requires modifications to the memory scheduling logic. In fact, significant modifications compared to what we're going to describe, because you need to rank the applications and you need to prioritize the applications. And these are actually not so easy to do. And later paper that builds on these works, Bliss paper, for example, quantifies the cost of this. I should have put a slide on Bliss, but maybe I will mention it later on. So this is one, cost, basically, significant hardware modifications. And the second is you cannot completely eliminate interference by just request reordering. So what the memory scheduler is doing is, it has a bunch of requests it has received. It's trying to juggle, right? It's trying to reorder one over the other to get good performance, essentially. But it has to deal with whatever it's presented. And those are the requests. It's juggling, basically. Okay, so if you want to completely eliminate interference between some requests, then maybe we need to take a different approach. Scheduling by itself, memory request scheduling by itself is not going to work. Okay, that brings us to the key approach and ideas. And please interrupt me if there are questions. So this is the first approach, basically. The paper introduces application over memory channel partitioning. And the observation is very simple, basically. Modern systems have multiple channels. In the past, there was only one memory controller on a single chip. But over time, people started putting many cores, but also they started putting memory controllers. Maybe not as many as the cores, because memory controllers are actually quite complex. They're big structures, and they require pins, meaning off-chip pins, channels. So there are not as many memory controllers as the cores, but I'm going to right now assume that these two applications have two cores have two memory channels, memory controllers. We're going to generalize it later. Okay, so clearly memory is partitioned into channels. So this gives us a new degree of freedom in terms of handling memory interference. And the degree of freedom is the mapping of data across multiple channels. How do you do that mapping? So let's take a look at how mapping is done in current systems. Basically, current mapping is not application aware. This red application has pages that are mapped to channel 0 as well as channel 1. This blue application also has pages that are mapped to channel 0 and channel 1. As a result, they interfere with each other in both channels, right? So this data mapping is clearly causing the interference. So if you were able to magically partition channels between applications, such that red application goes to channel 0, blue application to channel 1, then there would be zero interference, right, between the two applications, at least in the memory channels. There might be interference in the caches, but that's not the target of this work. The target is really a deal with the memory interference in the memory controller. Okay, so hopefully that's clear. Basically, partitioning the channels between applications lead to eliminated interference. But of course, this may not be, this is luxurious, right? You don't have enough channels to dedicate one to each application to. Clearly, that's one downside. You need to, you have more applications running than you have memory channels usually. For example, you may have a 24-core system and 4 memory controllers. You may have a 1,000-core system with 16 memory controllers. That's a possibility. So you don't have this nice picture that I showed you over here. And also, when you do this partitioning across channels, you partition the memory capacity as well. And that's something important. And you may start getting page faults, for example, because this application doesn't have enough memory capacity. So rigid partitioning, very rigid partitioning that doesn't allocate to an application from channels other than the ones it's assigned to, is not a good idea also, as this paper also discusses. We're not going to talk a lot about that, but the paper discusses those issues. Okay, so let me give you the overview. I gave you kind of the key observation. Now let's talk about memory channel partitioning in a little bit more detail. So the goal is to eliminate harmful interference between applications. And the basic idea is very simple. Why don't we map the data of badly interfering applications to different memory channels? And the paper then introduces 2 key principles as to how you would separate the applications, because there are not enough memory channels to assign each application to. And even then, it may not be a good idea to really give one channel to one application, because again, application may need more memory. Let's cluster, or let's categorize applications based on some key principles so that we can partition the memory channels across types of applications. And that's the idea over here. So basically, there are 2 key principles that this paper introduces: separating low and high memory intensity applications. And you could argue that this is not new. This is similar to thread cluster memory scheduling. And that's true. The paper is going to use that principle to partition the channels. And the second principle is separating applications with low and high roboffer locality. And you could argue this principle is also not new. Basically, the paper comes up with 2 principles, but it's rooted in prior work. But what it's going to do with those principles is going to be different. Okay, so let's take at this insights, basically. Separate by memory intensity. The insights apply to the memory channel partitioning, basically. So high memory intensity applications interfere with low memory intensity applications shared memory channels. So let's take a look at this simple example. You have the red application and blue application. And I'm going to see the timeline of requests over here. Red application sends some requests. Blue application also sends some requests. And they interfere with each other in the channels, right? So this is one example, right? If you do conventional page mapping and don't partition the channels. Now let's take a look at an example where we partition the channels between these 2 different applications. This is just, again, a motivating example to derive the principles. If you partition the 2 applications to different channels, and if you put the low intensity application separate from the high intensity application, this is what you get. Basically, the performance of the low intensity application improves significantly because its request does not get delayed behind many requests of the high intensity application, as you can see. And also in this particular case, the performance of the high intensity application also improves, as you can see, but not as much as the performance of the low intensity application. You can see that you save a lot more cycles for the blue application than you save for the red application. So hopefully this is clear, right? Basically, the first principle is map data of low and high memory intensity applications to different channels and group applications such that low and high memory intensities go to different groups. Basically, separate by memory intensity. Okay, now let's take a look at the second key insight principle. So high roboffer locality applications interfere with the low roboffer locality applications shared memory channels due to first ready, first come, first served scheduling, which prioritize row hit requests over other requests, right? Let me again show you an example. With conventional page mapping, 2 different applications with 2 different row buffer localities go to essentially interfere with each other in the same channels. So you can see that the red application has higher row buffer locality, R0, R0, and blue application has essentially random access to different rows. Okay, and you can imagine the red application being even more intensive if you wish. So basically, because the row buffer locality of red applications requests are higher, they go to the same row, the memory controller prioritizes them. And as a result, the blue application, even though it's higher intensity in this particular case, gets delayed significantly because the application has less row buffer locality, or no row buffer locality in this particular case, right? Okay, now let's take a look at what happens when we partition the channels between these two different applications. Again, the performance of the application that is interfered with improves a lot. Even though this is a higher intensity application, this has lower row buffer locality, but you improve its performance by separating it from the application that is interfering with it. A lower intensity application is interfering with it. It has fewer requests, as you can see. That application's performance does not improve. You don't lose anything. You gain a lot on this application, basically. So, okay, of course, clearly these are cooked up examples to motivate. And in this case, we motivate that you want to map the data of low and high row buffer locality applications to different channels. And we're going to use these two key principles to develop mechanisms for memory channel partitioning. And that's what I'm going to move to next. Now, let's take a look at the mechanism in some detail, right? And this is called memory channel partitioning. And the mechanism consists of 5 key steps. The first of which is doable in hardware, requires hardware support, and everything else can be doable in software, basically. So basically, we would like to profile the applications to figure out their characteristics in terms of miss rate and row buffer locality, intensity and row buffer locality, I should say. And then we want to classify applications into different groups. We will see how to do that. And we want to partition channels between different application groups as opposed to individual applications, because the hope is that applications within the same group do not interfere with each other that much, at least badly, very badly. We want to reduce the bad interference. And then we're going to assign a preferred channel to each application. It's just a preferred channel. If the application needs more memory, it may go to some other channel. So it's a best effort mechanism. And then we're going to allocate application pages to the preferred channel. So among all the steps, only profiling requires some hardware support because it requires understanding of the row buffer hit rates of the applications as well as memory intensities, some of which may be done in some systems with hardware counters, but many systems didn't have the hardware counters we were looking for at the time. And the rest can be done in system software. So it's really a hardware software cooperative solution. Of course, you can put some of the system software tasks into the hardware as well if you think they're time critical. But in this paper, as proposed, they're system software. Okay, now let's take a look at each of these steps in a little bit more detail. So the first step is profiling applications. So you need hardware counters to collect application memory access characteristics. And memory access characteristics is twofold in this case: memory intensity for each application, last level cache misses per kilo instruction. Basically, you can easily compute this inside the core, essentially, or the memory controller as well, and communicate this to the software using performance counters. And the second is row buffer locality, essentially row buffer hit rate. This is the percentage of accesses that hit in the row buffer. And this is a bit more cumbersome, but you can read the paper for more detail as to how to do it. Okay, and you want the inherent row buffer locality, so this requires more hardware support than what is provided in existing systems, because you don't want the row buffer locality after interference has affected row buffer locality rate. Okay, so the second step is classifying applications. So we have assumed that we have these two, MPKI and RBH. These are the two characteristics that we want to know for each application. To classify, we want to test the MPKI first, and we want to group the applications in terms of low intensity and high intensity. And among low intensity applications, the paper says it doesn't matter, basically. You may have high row buffer locality, row buffer locality, it doesn't matter as much. It's better to group the low intensity applications by themselves. And then among the high intensity applications, row buffer locality matters a lot. Remember, these are mice. Between the mice, among the mice, maybe it doesn't matter the characteristics. And this was actually an observation of past papers also. This paper validates that and basically carries it over. But among the elephants, the high intensity applications, there are some intense applications that have high row buffer locality. There are some applications that have row buffer locality, and you would really like to separate them to different channels because given the row buffer hit first based prioritization mechanisms that are employed in the memory controllers, the applications with high row buffer locality will deny service or reduce the performance of applications with low buffer locality, like we have discussed earlier, right? So basically, between the elephants, low buffer locality matters significantly because, again, these are huge elephants. If you prioritize one over the other significantly, then you may actually kill one of the elephants, right? I know it's not the nicest analogy, but that's how it is. Your performance gets destroyed. Maybe the elephant cannot move, right? Okay, so basically the third step after classifying the application into 3 different groups, in this case, we have 3 different groups, as you can see, as color-coded also. We want to partition channels among groups. And again, we have 3 different groups, low intensity and high intensity. And we have N channels. Then now this is a mapping problem and partitioning problem. And the paper explores different methods. I'm not going to go into all of them. It first partitions the channels between low and high intensity applications based on proportional to the number of applications in each group. You can actually question this. This is, I think, a weakness of the paper. Proportionality to the applications. Okay, it may make some sense to protect the low intensity applications, but what if you have a lot of applications over here in the low intensity group? Then you will underutilize these channels. But that's how it is. The paper proposed a mechanism that works. Maybe there are better mechanisms going into the future. Okay, so that's the mechanism. Now low intensity applications get some number of channels. Now, what do you do between the number of channels that are assigned to high intensity applications? Now you further partition them based on the low buffer locality characteristics of the 2 different groups. And here you assign number of channels proportionally to the bandwidth demand of each group. So you basically figure out what's the bandwidth demand of this, what's the bandwidth demand of this, and proportionally assign channels. I'm going to give you an example. And in the end, you get essentially a partitioning that looks like this. Some of the channels go to low intensity applications. Some of the channels go into high intensity, lower buffer locality. Some of the channels go into high intensity, higher buffer locality. Okay, my computer slowed down a bit. Okay, maybe I'm not going to give you an example, but you can see the example in the paper. And then the next step is assigning preferred channels to each application. Now you have applications partitioned into different groups and channels assigned to each group. And now you have preferred channels for each application. And the next step is assign it. You distribute applications to channels such that group's bandwidth demand is balanced across its channels. Okay, maybe I have an example over here that's similar to the example that I was going to give you. So for example, in the low intensity group, if the low intensity group is assigned 2 channels and low intensity group has 3 applications, each of them have different intensity levels, misses per kilo instructions 1, 3, 4 over here. Basically, you try to balance the bandwidth demand. You basically assign these 2 applications with MPKI 1 and 3 over here, such that the bandwidth demand is balanced between the 2 channels. And you basically sum up the MPKIs. It's kind of hacky, but that's a simple way of trying to balance the bandwidth demand, basically, simpler than prior approaches. But yes, it is hacky, basically. You could argue that, okay, you're adding up MPKIs where the I's may not be equal, for example, right? Because they're executing different instructions. So from a theory perspective, it's hacky. But from a practice perspective, it's easy to do. And it works, as the results will show. But you can always do better by optimizing these steps potentially. Okay, so hopefully it's clear. The sum of MPKIs across each channel are, you try to make them equal by assigning preferred channels. Again, this is a preferred channel assignment, meaning if you're running out of memory in one channel, you can use some other channel. This brings me to another question, basically. How do you do the page replacement policies? And the paper tackles that briefly, but there's a lot more work that can be done in this area. Okay, now the 5th step, the final step, is allocating page to the preferred channel. Basically, you want to enforce channel preferences computed in the previous step. Every application has a preferred channel. How do you do the enforcement? On a page fault, the operating system allocates page to the preferred channel if free page is available in the preferred channel. Otherwise, replacement policy tries to allocate page to the preferred channel. If it doesn't work, then you allocate page to another channel. Here, there's a lot of design space that comes up, and the paper, I don't think it explores it fully. I think that's a downside, but it may be hard to explore this design space fully also, because now you're running into page replacement policies that are channel aware, and there may be many different types of policies over here for multiple applications. And I think this is actually an interesting area of future research, because there's not been a lot of work in this area going forward, because it's at the operating system hardware interface. And unfortunately, this interface has not been tackled as much in the past. well, for various reasons. One of the reasons is, in general, when people write system software, they don't want to assume too much from the hardware, for example, and they also are not aware of what's going on in the hardware internals, and we don't have very good interfaces as well. So I think this page allocation and replacement policies with multiple channels in place that are aware of interference, etc., are quite important going into the future. Okay, now I described the 5 steps of memory channel partitioning. Let me give you the overall operation. Where do these 5 steps fit? Basically, we operate based on intervals. If you think of execution of a system in terms of this timeline, you chunk it into intervals, and intervals are fixed time. In this particular case, you can read the paper for how long it is. They're quite long, 10 million, 20 million instructions, cycles, for example. You basically profile the application in the current interval. And at the end of the interval, you classify the application into groups based on the profiling information you collect. And then you partition the channels between the groups, and then you assign preferred channels to applications. So everything we described happens at the end of the interval. And for the next interval, you enforce the channel preferences, as we discussed. Whenever an application gets a page fault, you allocate from the right place. Okay, so hopefully that's clear. Of course, you can pick on this implementation also. Why is it time-based intervals? Why isn't it something else? That's good for a potential discussion, right? Okay, so that's the memory channel partitioning mechanism. Remember, the prior approach was memory request scheduling. Now this paper introduces memory channel partitioning. And this paper also says, identify some issues with pure memory channel partitioning. So it's going to introduce another approach called integrated memory partitioning and scheduling. And let's take a look at that now. So the paper is motivated by 2 observations, basically, to go into the next step. First, applications with very low memory intensity rarely access memory, meaning that if you actually dedicate channels to them, you waste precious memory bandwidth. Why? Because they count as one of the applications, and whenever you do the partitioning of the channels, they basically count as one of the low memory intensity applications, even though they really rarely access memory. So it's probably better to do something else with them. And also the paper realizes, similar to prior work, that these applications actually have the most potential to keep their cores busy. So if you're not very intensive, you really want to prioritize those applications. You don't want to partition the channels because you don't want to waste bandwidth. You just want to prioritize these application requests whenever you see them. And that's the idea, basically. Why? Because they also minimally interfere with other applications. So this is the third observation that I mentioned earlier. If you're not generating a lot of requests, you're likely not interfering with other applications. So prioritizing these applications doesn't hurt other applications. Okay, so based on these 3 observations, the paper proposes this idea of integrated memory partitioning and scheduling. And the idea is very simple again. With very small modifications to the memory controller, you always prioritize very low memory intensity applications in the memory scheduler. Of course, you need to have a cutoff. Right now, you need to cluster the applications between very low memory intensity, and high memory intensity. And then for the remaining applications, low memory intensity and high memory intensity applications, you use the memory channel partitioning, as we discussed and described. Okay. So if everything is clear, now we can move to key results. And I'm going to talk about methodology and evaluation. I'm not going to go over all the results in the paper. There are a lot of results in the paper. I'm going to just give you the key takeaways and key results, and then move on with the discussion. Okay, so basically, let's before we talk about performance results, let's talk about hardware cost results. Essentially, memory channel partitioning requires only profiling counters in hardware. There's no modification needed to the memory scheduling logic. So in that sense, it's very low cost. So you can see the storage cost is very low for a large system. Integrated memory partitioning and scheduling requires a little bit more support from the memory scheduler. Basically, you need to have one single bit per request saying this request is prioritized because it's from a very low memory intensity application. And scheduler basically prioritizes based on the single bit. If you see a request with this bit set, that's the highest priority request. The second prioritization order is row buffer hit first. The third is oldest first. So this basically adds another level to the prioritization mechanism. And hopefully that's simple to understand as well. So it's very little cost, actually. The paper quantifies the cost. I didn't put it over here. So basically 1 bit per request. Okay, so the paper does this in simulation because there is no hardware that implements the proposed hardware counters, let's say. If the hardware counters were there, the paper could have done a real system work study, but It's very difficult to do the study in real system. Well, not possible to do the study in a real system, let's say. At least a general purpose system. You could have some special purpose system where you can construct, but again, this is 10 years ago. Okay, and you can see that this is the main model, 24 cores, 4 channels, 4 banks per channel, and these are some heavyweight cores. And at the time, we used DDR2, which is old, as you know. And the workloads are basically, the paper evaluates a lot of randomly generated workloads. I mean, these are real workloads, but the mixes are random. So you, for example, run different types of workloads together so that you can see the effects on general purpose workloads. You can think of this as somebody throws workloads to the cloud, and many workloads get run together in the cloud, and it could be anything basically. And it's categorized based on memory intensity. The paper has a lot of results in terms of memory intensity. By categorizing the workloads based on memory intensity of the overall memory intensity of the workload, you can gain insight into how the mechanism is working. For example, this mechanism is not going to be very useful if the memory intensity of the workload is low. It's also not going to be very useful if the memory intensity is going to be extremely high potentially. But that's not in the medium memory intensities. That's where you get the highest benefits. And there are some metrics that I'm not going to talk about. These are multi-program performance metrics that many papers use. Okay, and the paper compared to prior work in memory scheduling. This is first ready, first come, first serve, which we discussed. It's application unaware. Atlas is one memory scheduler. It prioritizes application with low memory intensity. And this is actually a relatively low cost compared to thread cluster memory scheduling. Thread cluster memory scheduling was the state of the art at the time. And we discussed how it works basically. And if you look at all of these, they have downsides basically. Paper compares to all of them. And this is a huge average across 240 workloads. So that's why the numbers are low. If you look at individual mixes, the numbers can be high. But we're looking at an average over here. And FRF-CFS is here. The performance is normalized to FRF-CFS. And basically, on top of FRF-CFS, if you implement just memory channel partitioning, you get significant performance improvement, better than prior memory schedulers, as you can see, with no modification to the memory scheduling logic, memory controller essentially. And on top of this, if you implement integrated memory scheduling and partitioning, the performance improvement increases even more with very simple change to the memory controller. So overall, the idea is effective clearly. There's significant performance improvement over baseline FRF-CFS, and also significant performance improvement averaged across many applications again over the best prior mechanism, memory channel partitioning. So the thread cluster memory scheduling, right? And these numbers may seem low, but they're big averages. Okay. Basically, you get better system performance than the best previous scheduler at lower hardware cost, significantly lower hardware cost, I would say, because later papers showed that a scheduler like thread cluster memory scheduling is actually quite costly in terms of hardware. Whereas integrated memory partitioning and scheduling is very little hardware cost. It's just 1 bit per request and prioritization using that bit. Okay, so clearly there's interaction with memory scheduling also, which the paper points out. So basically, memory channel partitioning and IMPS, integrated memory channel partitioning and scheduling, is designed for the first ready, first come, first serve policy, because it doesn't change the memory controller, memory scheduling policy that much. Whereas other scheduling policies are very different in terms of how they operate. So let's take a look at what happens if you implement IMPS on top of other scheduling policies. So this is our baseline, FRF-CFS. You can see it's 1.0. And this is Atlas, and this is TCM. And clearly these ideas improve performance to some degree. And if you don't implement IMPS, if you implement integrated memory partitioning and scheduling, the highest performing system is a system that employs first ready, first come, first serve scheduling. So the other memory schedulers become not as effective, let's say, or the compound benefits with of another memory scheduler plus the integrated memory channel partitioning and scheduling is not high enough compared to the compound benefit of FRF-CFS, a simple memory scheduler or relatively simple memory scheduler, plus IMPS. Okay, so this is interesting, right? What's going on? Basically, there's first observation. It doesn't matter what your baseline memory scheduling policy is. IMPS is providing performance improvements. But if you dig deeper, highest performance improvement is over first ready, first come, first serve, as IMPS is really designed for first ready, first come, first serve. Remember our key insights. prioritizing low intensity applications over high intensity applications, and also partitioning channels between low intensity and high intensity, partitioning channels between low buffer locality and high buffer locality. Those are all based on the fact that existing memory schedulers cause interference by doing something not good with those applications, basically. You create these mice and elephants by doing something not good in the memory scheduling. But some other memory schedulers are designed to actually fix those problems. As a result, they operate based on completely different principles. As a result, a memory channel partitioning policy that uses the principles that are inferred from first ready, first come, first serve is not going to work as well on those memory schedulers. And that's these results kind of validate that. What the paper doesn't do is to go and figure out a memory channel partitioning mechanism that's designed for these other memory schedulers. I think it's interesting, but that's where the paper stops, basically. Okay, so hopefully that's clear. Okay, now let me summarize. We're at the end of the summary part. Basically, this paper tackles the problem of uncontrolled inter-application interference in the main memory. That uncontrolled application interference degrades system performance. And the paper proposes application of our memory channel partitioning, which separates the data of badly interfering applications to different channels, eliminating the interference between applications that go to different channels. And it also builds the integrated memory partitioning and scheduling policy, which prioritizes very low memory intensity applications in the scheduler and handles other applications interference by partitioning, MCP basically. And both channel partitioning and integrated memory partitioning and scheduling improve performance more than application of our memory request scheduling, while also at the same time having much lower hardware cost. Okay, so that's the summary basically. Any questions on the mechanism, problem, results, etc.? Hopefully it's clear. No, it sounds like everything is very clear. Hopefully that's the case. Okay, then let's move on to analysis. And this is maybe even the more fun part, right? Clearly, like every paper, this has strengths and weaknesses. Let's start with the strengths. Again, conceptual strengths are the best to begin with. So basically, this is a novel solution to a key problem in multi-core systems, which is the problem of memory interference and degrading system performance. And the importance of the problem will increase over time, basically, because memory bandwidth is going to be a bigger and bigger bottleneck because we can put more cores on a chip, whereas we cannot put more pins, at least at the same scale, at the same rate as we can put computational units that can generate memory accesses. Keeps the memory scheduling hardware simple, and this is one of the first approaches that looks at that. Basically, maybe it's the first approach actually that tries to keep the memory scheduling hardware very, very simple. It recognized the problem of handling memory interference in the memory controller solely as a hardware costly problem, and it tries to avoid that. It combines multiple interference reduction techniques. So this is also the first paper that combines memory channel partitioning as with memory scheduling, for example. It can provide performance isolation across applications mapped to different channels. If the application is complete, they're isolated in different channels, your performance doesn't get affected by that application. But the paper mentions this, but doesn't evaluate this in detail. And the general idea of partitioning can be extended to smaller granularities in the memory hierarchy. So you can partition banks across applications, you can partition subarrays across applications, potentially you can partition row buffers if you think differently across applications. So basically you can extend the higher level conceptual idea to different granularities and levels in the memory hierarchy. And I think that's interesting because we're going to talk about some future work that did it exactly. Okay, so these are some, I guess, conceptual and idea-related strengths and novelty-related strengths. I think it's also a well-written paper. Again, don't take my word for it. Go and read it. And the paper does thorough simulation-based evaluation, but you can always question how thorough is thorough, right? But I think compared to many papers in the field, the thoroughness of the paper is quite strong, let's say. Okay, those are strengths. Maybe there are some other strengths that I didn't think of, or if you come up with something, please let me know. Feel free to chime in. Now let's go to weaknesses, and you can still feel free to chime in whenever you think of a strength or a weakness, let's say. But let's start with the weaknesses. Clearly, this is an important part. This is where critical thinking comes in, right? Because most papers don't talk about their weaknesses. And this paper actually talks about some of the weaknesses because it says basically channel partitioning is not good under some conditions, right? And these are the conditions. And I'm going to repeat some of them later. I already mentioned them actually, but let's start with some of the important weaknesses. Basically, mechanism may not work effectively if the workload changes behavior after profiling. And this is always a problem with profiling-based methods. And this paper is no stranger to this problem because it's also a profiling-based paper, right? It profiles the applications. It's basically categorized the application based on that profile. If the application profile changes for the next interval, well, too bad. You got the wrong profile, but that's how it is. And again, any profile-based mechanism is vulnerable to this problem, and there's no easy way to fix this problem, let's say, unless you profile at a finer granularity, or you figure out the workload behavior changes, or you profile in a different manner. For example, this employs time-based profiling. Maybe there's an application-driven profiling methodology that detects when an application changes behavior and reprofiles at that time, right? I think there are potential solutions to this, but they all come with different costs. Okay, so the second issue, there could be overhead of moving pages between channels. I don't know why my computer is again slow, but it is slow. But basically, whenever you want to move pages, so for example, you partition the channels to applications in some way. In the next interval, you want to change that partition. If you want to change that partitioning, now you need to move the pages from one channel to another. Again, you can do it lazily. You can do it eagerly. Eagerly meaning you move all of the pages belonging to an application right away. Lazy is probably a better idea if you don't want to disturb the system that much. But again, this data movement across channels is very heavy. So the paper basically discusses it and says that it's not a good idea to do this in general. So basically stick with the preferences and just allocate the new pages from the new preferred channels. Don't touch the old pages, basically. And clearly, this restricts the mechanism's benefits, right? The trade-off is you're using some stale, according to the principles, stale channel assignment to the application to avoid the large data movement costs across channels. And the paper's preference is we want to avoid the large data movement costs. And maybe that's a good preference, but still, what I wrote over here is true. You restrict the mechanism's benefits. Okay, and small number of memory channels reduces the scope of partitioning, and that's absolutely true. If you have only one channel, the solution is clearly not applicable, right? If you have two channels, it's less applicable. If you have 16 channels and maybe 24 applications, clearly that's more applicable right now, right? So the number of channels affects both the scope as well as effectiveness of the mechanism. Okay, that's not true for memory request scheduling, for example. Memory request scheduling doesn't care how many channels you have, right? Here, you're dependent on the number of channels. And also, actually, the second one is also not true for memory request scheduling. There's no page movement, data movement required in memory request scheduling. The first one is true for memory request scheduling as well. But again, when an application changes behavior in memory request scheduling, you can adapt relatively easily. You just need to change the prioritization order. You don't need to move pages, for example. Okay, load imbalance across channels can reduce performance, and the paper clearly acknowledges this, right? The paper says we don't want to cause load imbalance, but some load imbalance is inevitable if you want to really partition the applications across different channels. And clearly, this affects the performance, actually. So you don't utilize all of the channels very effectively with this mechanism. And that's true for, again, general partitioning mechanism. Whenever you partition resources, your utilization of the resources goes down. Okay, and I said that the paper actually addresses this and compares to another mechanism that I'm not going to talk about. There's another mechanism that was published in 2010 that tries to load balance. And this paper shows that you don't want to just do load balance, you also want to do partition. Okay, partitioning and load balancing are actually two interesting aspects of dealing with memory channels. And this paper argues that you need to employ, our paper, memory channel partitioning, argues that you need to employ both of them. And shows basic benefits over this prior mechanism that just does load balancing across memory channels. Because if you just do load balancing across memory channels, you're not aware of the interference between applications, right? That's the idea. Okay. Okay, let's see other weaknesses. Okay, there are some other weaknesses, like maybe some more rat hole type of weaknesses, just to warn you. Clearly, there's some adoption issues because it's a software-hardware cooperative solution. You need to change the hardware, change the software. Even though the hardware changes are less compared to many memory controllers, still there's some hardware changes as well as software changes that are required. And clearly, whenever you do cross-layer optimization, these optimizations may be difficult to adopt because you're changing a lot. Okay, evaluation is done only in simulation, and that's true again. Potentially, this could have been done on a real system with proper reverse engineering, but that requires more effort, clearly. And again, you may not be perfect. Simulation, you're controlling a lot of variables in simulation, so that enables you to study a particular idea and do justice to it by controlling the environment, right? In a real system, you may not be able to control the environment perfectly, especially if you do not know what addresses get mapped to what channels, right? And also, if you do not know, if you do not have enough information about characteristics of the applications like memory intensity and robot for locality, which is the main reason why we didn't do it in real systems, because we didn't have access to robot for locality characteristics of the application in a reliable manner. Okay, now we can actually go to even more like evaluation issues. We're getting closer to rat holes, so you may mention them, but maybe not go into a lot of harping on them. So evaluation doesn't consider multi-chip systems, and that's true. I don't know how relevant it is, but it may be relevant on large-scale system. And are these the best workloads to evaluate is some question that you can ask for any paper, basically. The paper takes the approach that we want to look at general purpose workloads. So we create these mixes of multi-program workloads where we randomly pick an application and basically couple it with other randomly picked applications. Okay, is that the best type of workloads to evaluate? Maybe there are some other workloads where you can actually show the benefits of this approach better. I believe that's the case, actually. We were just agnostic, basically. We just did it randomly. We randomly sampled the workloads, essentially. Okay, so hopefully, I mean, you can also raise a lot of other issues in evaluation, but I'm not going to go through that. I'm going to go to the next slide, which has our favorite rats. But clearly, my Zoom is going too slow. But basically, try to avoid rat holes. So workloads, these issues that we discussed in prior lectures, like metrics, configuration, specific evaluation details, etc. They all can lead to rat holes. It's good to mention them in weaknesses, but these are not in general great ideas, good ideas to reject papers, as we also discussed in the last lecture, right? Okay, so now let's go into more thoughts and ideas. Are there any questions? Today people are quite silent. Okay, I don't see any questions in the room. Are there questions in Zoom? Okay, I don't see any hands. So let's go into thoughts and ideas, basically. Let's talk about some extensions to this. So basically, can this idea be extended to different granularities in memory? And the answer is yes. This is more or less a rhetorical question. Basically, you can extend it to bank level. You can extend it to subarray level, even math level potentially. Can this idea be extended to provide performance predictability and performance isolation? If so, how? I think there needs to be more research to be done in this area. But memory channel partitioning is a good idea for isolating to applications also, even though this paper doesn't really use the partitioning mechanism for that purpose. So it's good for quality of service. How can memory channel partitioning be combined effectively with other interference reduction techniques like source throttling methods, like thread scheduling methods at the system software level, like other memory request schedulers in a better way, like we discussed? So clearly there are other interesting things here. I'll mention source throttling in a little bit and give you a pointer to a paper. I think that's another exciting idea, basically. You can partition channels, but maybe this work has proposed throttling the cores. If a core is causing a lot of trouble, a lot of interference to another core, throttle the requests of that core, basically. Don't allow it to actually send so many requests to the memory system. And that's clearly another way of dealing with interference. And how do you combine it with memory channel partitioning mechanisms is interesting. Okay, and then the last question, maybe there are other questions, of course. Can this idea be evaluated on a real system? And if so, how? And I think this is still a good question to ask. Although I think even though it's been 10 years, it's good to understand the capabilities of a real system today. And again, I think the operating system hardware interface has not evolved nicely that much, if it has evolved at all, let's say. Basically, operating system doesn't know the topology of memory, DRAM very well. It may know the channels, okay? It doesn't know the banks. It doesn't know the subarrays. it needs to reverse engineer all of that. Yes, we can reverse engineer a lot of that, but unfortunately, we don't have a great interface between the operating system and the hardware, so that the operating system can basically do what we have discussed and actually allocate pages to different channels and different banks and different subarrays. So I think this idea is evaluated on a DL system today. We should really look at different granularities as well. Okay, and this is the source throttling paper that I mentioned. This is the application of our source throttling. We called it fairness via source throttling. And the idea is very simple again. Detect which applications are causing interference to others and throttle down their accesses such that their cores don't generate as many requests. Of course, the devil is in the details. How do you do it exactly? Well, I'll refer you to the paper. I'm not sure if we have this paper as one of the papers on the list, but again, you can choose it if you're interested in this direction, and maybe you'll get assigned it. You'll get assigned to it depending on what your other preferences are and depending on what other people's preferences are. So we have a list of, I think, 60 plus papers that we have released. You have seen that list, right? Have people seen that list? Okay, I think I see hands up. So I got my feedback. That's good. So please fill out that form now that I'm reminded of it. Please fill out your preferences. And the more preferences you provide to us in terms of like, oh, I want this paper as a high priority, then we're more likely to accommodate your preferences. So if you provide one paper saying, I just want this paper and nothing else, and if somebody else also says the same thing, I just want this paper and nothing else, then we have a interference problem, right? Two people are conflicting on the same paper, and only one person can present one paper. We don't want redundant paper presentations. As a result, you will get assigned a paper that you didn't choose. So it's better to specify your preferences as flexibly as possible, let's say. Okay, if you have questions on that, we can discuss. But let's do the takeaways of this work. Basically, takeaways, it's a novel method to reduce memory interference. No paper discusses this before. It's simple and effective. It's hardware-software cooperative. And there's good potential for work building on it to extend it to different structures, like different DRAM structures, different metrics. So yeah, maybe this should be part of the weaknesses potentially also, right? Maybe, I mean, it was kind of, yeah, I didn't really fully mention it, but you could also pick at the metrics, right? Say, why do I only care about throughput, right? I also care about performance. I'm sorry, I also care about per application performance, meaning how much quality of service I'm getting. I also care about fairness. And the paper doesn't examine those metrics. And again, this is a fair criticism of the paper. But again, to be fair to the paper's goal is not that. The paper posed its goal as we want higher performance. And this interference is really causing problems for us in terms of achieving higher performance. So how do we design? How do we use a new idea like memory channel partitioning and integrated memory partitioning and scheduling such that we get higher performance out of the system? You could ask the same question as, how do we use this idea for performance isolation, for quality of service, for providing application slowdown guarantees, for example, compared to when the application is running alone? And clearly that is really expanding the idea and the mechanisms to different metrics. And you could view this as a weakness. And I think there's an argument to be made that this is a weakness. That's true. But it's not a perfect weakness because, again, the paper's goal is not to target those metrics. Okay, so multiple works I've already built on the paper. I'm actually going to talk about a couple of these very quickly. And there are other works that I'm not going to talk about. But there are a lot of works that built on this paper. You can find them online by figuring out what works actually reference this paper. But these works directly build on this paper. And I would argue that it's an easy to read and understand paper also, but please take a look if you're interested. So let's take a look at some of these works that build on this paper. So this is a paper that we published like a year later in HPCA in 2013. And here we're tackling at a larger problem. So memory channel partitioning tackles the problem at the memory controller level. Here we want to actually tackle even a more scalable system, meaning basically the idea is the application to core mapping to reduce interference. There are multiple key ideas, some of which are borrowed partially from this paper. We want to cluster threads to memory controllers to reduce across-chip interference, and also basically we're partitioning the threads across memory channels this way to reduce interference, off-chip interference as well. We want to isolate interference-sensitive applications in a separate cluster. So in a sense, a clustering idea is employed here also, but now you're actually trying to reduce interference from high-intensity applications. But you'll see that this is more spatial as well. because the mechanism is different here. You're really doing not only memory channel partitioning and memory controller clustering, but also mapping of the applications to cores. And you will see what that means in a little bit, because different cores have different latencies to memories in this case. And then we want to place applications that benefit from memory bandwidth closer to the controller, memory controller, so that we can improve performance of those applications. Okay, so basically, in a sense, memory channel partitioning is looking at multi-core systems. But if you go to many core systems, the system has some on-chip, significant on-chip communication as well. For example, let's take a look at this core over here. Let's say we have 4 memory controllers in this particular case, and we have a shared cache bank. Caches are distributed across the tiles, let's say, in the 64 tile system. Each tile has a processor and a cache slice, and cache is distributed, and things are interconnected via an on-chip network that I'm not going to talk about in detail. And the memory controllers are on the edges over here. There could be 4, but there could be 8 or 16 also. The important thing is there are not as many memory controllers as the number of cores again, right? Because these are costly resources. Okay, caches are shared but distributed. So physically distributed, but logically shared, meaning this core can place a cache block over here, another core may access it. Okay, so if this core requests a data, and if it happens to be in this cache slice, basically you need to go through the network to get the request from the core to the slice, and then you need to get the reply from the slice to the core. So there's some on-chip communication that's going on, as you can see over here. Okay, if you get a cache miss over here in the slice, things are not as nice. Basically, you do the request, and then the request gets sent from the cache slice to the memory controller that houses the block. And then the memory controller gets the data from main memory and then responds to the cache slice, and then the cache slice responds back to the core. So now you're increasing the round trip time. And as the chip grows, these on-chip interconnect latencies will also increase, as you can see. Okay, so now let's take a look at 2 applications. One is light and one is heavy. The light application is doing this. At the same time, okay, I didn't animate that, but at the same time, heavy application is heavily accessing this memory controller over here, or this memory controller over here. Basically, the request or this memory controller over here. Basically, if it's accessing this memory controller, it's going this way. If it's accessing this memory controller, it's going this way, and the results are coming this way. And if it's accessing this memory controller, it's going this way, and the results are coming this way. So there's some interference that you're causing. And this is assuming some routing policies, of course, right? There may be other routing policies that cause more interference. But clearly, this heavy application that injects a lot of requests to the memory controller can cause problems, interference to this light application that once in a while needs to access this cache bank and memory controller. And that interference is exacerbated, unfortunately. And the paper does a lot of studies that talks about it. Since we're not covering this paper, I'm not going to go into detail. But basically, this problem of memory interference between light and heavy applications and applications of different characteristics gets worse and worse as the system scales to more cores as well as more memory controllers, because there's not just interference in the memory channel but also on chip interference, which is similar in nature, but maybe not as much let's say studied by prior works. Okay, this work studies it basically, and basically it formulates the problem as spatial task scheduling. You have a bunch of applications with different characteristics. You have a bunch of cores. How do you map the applications to the cores to minimize interference, to reduce latencies, to maximize performance, etc.? Okay, so there are challenges here, basically. How do you reduce communication distance, basically minimize the communication latencies? How do you reduce destructive interference or bad interference between different applications? And how do you prioritize applications to improve throughput? And there are many things that this paper does. I'm going to go over it. In a sense, there are similarities between the prior paper, but except this paper, the newer paper, builds on memory channel partitioning to do something even bigger, let's say. So you can see that first idea is clustering, meaning cluster applications to different parts of the network, such that this application can access this memory channel and also this part of the network, and true for other applications. Again, don't do it in a hard, rigid manner. Do it in a preferred manner, like we did in the memory channel partitioning. So the good news is now you improve locality to reduce interference. This light application doesn't get interfered by this heavy application, right? They sit in their clusters and they don't destroy the performance of others. And again, this leads to a balancing problem, again, load imbalance problem. And the paper proposed a method to do this. Again, I'm not going to cover this. It has some similarities to memory channel partitioning, but it also has some differences. The next thing is to balance workloads across different memory channels and also network pieces, clusters essentially, to improve the bandwidth utilization. Some sort of balancing. And then the paper also says, oh, some applications need to be isolated, especially low memory intensity applications need to be isolated. So you want to get rid of some, you want to create some imbalance basically, so that some applications are isolated. So isolation always creates some imbalance basically, because you're partitioning based on the characteristics of the application as opposed to trying to balance the requests and balance the bandwidth across all clusters, let's say. And finally, the paper proposes the idea of putting memory intensive applications closer to the memory controllers such that they can maximize their memory bandwidth in this network, and also the network bandwidth. There's internal network over here. So, okay, these are 4 key ideas, and the paper describes all of them. But let's talk about clustering. Clustering is actually one of the interesting ones. So if this application was able to access all of the parts in the network plus all memory controllers, it would basically interfere with every other application, as well as it would be interfered by every other application in the system. So, and also at least inefficient data mapping to memory and caches. There are long distances, its latencies are longer, etc. If the chip is large enough, like why not do this? Why not partition into clusters and assign different clusters to different applications such that you minimize latencies for the application, but you also minimize by improving locality clearly, but you also minimize the interference between different applications. So you kind of kill 2 birds with 1 stone, right? By just clustering, you improve the latencies in this case, and also reduce interference. Okay, so hopefully that's clear. Even if the application is running alone, you improve the latencies basically. That was not the case with memory channel partition. Okay, and just to give you some results, this is the baseline. If you don't do anything, if you randomly map applications to cores, this is what happens if you add clustering. So clustering has a significant impact. And this is the performance results, what you get if you actually employ the full-blown application to core mapping mechanism as described. So you can see that clustering actually has significant impact. And these are different levels of intensity. So overall intensity of applications, the total misses per kilo instruction is 500 in this case. They're not very intensive. Still, you get significant benefits. These are some medium intensity workloads. You get significant benefits, as you can see. And this is the highest intensity workloads. You get slightly higher benefits, but it's similar. Basically, as long as you're at a reasonable level of intensity in your overall applications, overall mix, you get significant performance benefits. Let's say 20% or closer to 23% over here. Okay, but this is just one aspect of the equation, right? Okay, and that's the average. There's another aspect, which is power. So by basically prior work, you could also argue that memory channel partitioning work did not include power as a metric. And that's true. You could again say, okay, this is a weakness. And that's also true. Sure. But maybe we didn't have a good power infrastructure. Later, we built a nice power measurement infrastructure. And basically, we look at network power. How much power is spent accessing essentially main memory and the network? And this is what we see. Basically, baseline is 1.0. If you do clustering, it buys you significant power reduction. If you do everything that we described in application to core mapping, in addition to clustering is very similar to memory channel partitioning. It's also network partitioning, of course, not just channels. But you get significant, even more benefits. So basically, network power gets reduced regardless of the intensity of the applications. Even if the applications are low intensity, that's fine. Network power gets reduced because you're limiting how many accesses they're doing to the entire chip. Okay, so hopefully this is clear. Okay, and this is one work that builds on the ideas that were discussed in memory channel partitioning. And if you're interested, I'd recommend looking at it. I don't think this is one of the works that are in your potential, let's say, presentation list. Okay, yeah, I think there are other works also. This work is from UT Austin, HP, and ARM, as you can see. And they basically show that you can do bank partitioning. So they go one level beyond. And they basically talk about bank partitioning and say that that granularity gives you another degree of freedom, because you may have limited number of channels. Maybe you have only 4 channels, but each channel may have let's say 64 banks, right? If you can have 4 DIMMs, and each DIMM may have 16 banks each, that's 64 banks. And you have 4 channels, that's 256 banks. So now you have, as you go to finer granularity, you can partition the applications better across the DRAM banks. And that's what this paper talks about, basically. And it also talks about other things, but I'm not going to go into detail. This other paper actually shows you can actually do the bank level partitioning using software mechanisms. And I would recommend taking a look at it, and show significant benefits. And maybe there are some other papers later on that show some subarray level partitioning. And I think that's also a good idea to look into going into the future. Okay, but I don't have all the papers listed over here. If you find something, please let me know. I think this is fascinating. Okay, I think this is the generic thoughts slides. And I don't have any more slides. And this is where I will probably open to discussion. Do people have any ideas on this topic? Anything other than what I've discussed? Any other strengths, weaknesses, new ideas, new problems? It's a very silent day today. Anyone? I see the room is silent, so I don't hear anything. If there's nothing, then we can conclude the session early. I will wait for, let's say, a short time. So this paper, while I'm waiting, maybe I should say, this paper was not as unlucky, let's say, as the other papers that I mentioned last time, right? They were rejected multiple times. This paper was rejected only once, I think, before it got accepted. People liked the idea in general. Maybe it got rejected twice before it got accepted. I don't remember now. It's been such a long time, right? And I think the comments were, let's say, not as egregious as what I showed you last time. Even though I think there were some comments that were concerning. For example, one comment was, I think it was rejected twice. One comment was basically saying that, oh, why don't you do this on a real system? And basically, it's not possible. The way we envision it, at least. And the second comment was a little bit close-minded, basically. This is a conference about computer architecture, but you're modifying the operating system. We don't want that. Some reviewer said that, basically. Clearly, that's not very open-minded. Actually, there are a lot of works that cross the hardware-software boundary. And we need even more works that cross the hardware-software boundary going into the future. And certainly the operating system architecture boundary going into the future. But you can see that we received that comment, and that was one of the reasons why we got rejected from one of the conferences. I think it was ISCA. But it got accepted to Micro, as you can see right afterwards. So I think the comments were not as egregious as the last ones. But I think there's some, let's say, closed-mindedness in the best case. Okay, I don't see any other hands going up or any questions. Then I think we're going to conclude right now. Please fill out your preferences for papers and be as flexible as possible. We will start the paper assignments, and I think we will start seminar presentations from you, I believe, November 4th. Is that correct, Mohammed? Yes, okay. I see a hands up from Mohammed. So people who are going to be lucky to present first will have enough time. That's about, let's say, 3 weeks from today. Well, from the paper assignment, it's going to be more than 2 weeks. So that's going to be plenty of time to prepare your talk. But of course, we'll take that into account, right? People who present first are going to have less time to prepare compared to people who present later in the semester. But let's make sure that we have good discussions in the papers. Hopefully, we will have a very interesting set of papers. You see that they're going to be varied. I think our oldest paper that I put up was from 1969. You can pick that if you want. You'll see that the language is very different. And our newest paper is from 2021. In fact, some of the papers are not even uploaded because they're not public yet. But if you're interested in potentially selecting that paper based on the title, and if it piques your interest, please select it, because I think those are papers, actually, they're all interesting papers. So you don't have to look at the PDF because they're not publicly available at this point, but they're going to be available next week, for example. Okay, I think with that, we're done. Thanks. Have a good weekend, and we'll communicate with you what happens next week. There may not be any session next week, depending on all the preferences handling and when we start the first session. But it's likely that we're not going to have any session next week, and we'll communicate over email. Okay, take care. Have a good weekend. Bye-bye.